Okay, so say we have these permanent magnets that create a magnetic field that looks like this. We put a coil with N turns in between the magnet. And, in general, flux, let's say the magnetic field is constant. So we can say the flux in general is a dot product of B and A, or BA cosine theta, where theta is the angle between the normal vector. So like in this orientation, this A vector is pointing outwards and B is in that direction. So here, theta would be 90 degrees and cosine of 90 is 0. So again, the magnetic field lines are going along this surface. Nothing is passing through it. And so, we get 0 flux. If we rotate this 90 degrees, then the area vector and the magnetic field are lined up. And theta would then be 0. Cosine of 0 is 1. That gives us our maximum flux. And so let's say we place this coil here, and now we rotate it. And so what is the EMF going to look like? So our flux is NBA cosine theta. Cosine theta. So let's look at the EMF. It's going to be minus the derivative of this. Now, theta is the angle between the area and the magnetic field, or the normal vector and the magnetic field. Let's say we rotate this at an angular frequency omega, which we can say is theta times t. So just by picking the right t, we can say that theta is omega times t. So at t equals 0, theta is 0. Again, it doesn't really matter when we start the clock. But in general, we have theta is omega t. So let's actually replace this here. So the flux depends on time. And so if we rotate this coil at a particular rate, then we have the EMF is minus NBA. Those are constant. So we just take them out of the derivative. Derivative of cosine is minus sine. Well, minus, and then by the chain rule, we have this omega. So we get an EMF that looks like this. If we plot the EMF, the EMF is going to look like that. Now let's say we wrap this coil. Let's say we connect it to some device, like an ammeter. What's the current going to look like? Well, the current is going to look like this as well. And so we call this an alternating current. And this is what we typically, I said this is an important application of Faraday's law. And the reason is that this is how we get power, almost entirely through this process. What we're doing is we are turning mechanical energy. We have to rotate this coil. And by rotating it, we're producing an alternating current. So the current will look like this. If we just have, like we wrap the ends of the coil to an ammeter, our current will look like that. So it's alternating current. And again, think about like when you plug things into your outlet, this is what the current looks like. There's a device called an oscilloscope, which you could use to actually plot it, and you can actually see this is what the current or the voltage look like when you plug something into an outlet. But again, like, how do we actually get electricity? Mostly it is through burning things, actually. Like, you can burn coal or oil and just use that to heat steam. And steam, if you run it through a turbine, that's going to cause the turbine to rotate, and then you can attach a coil to it. And so, yeah, the point is, again, we have conservation of angular momentum. So let's say that there's no friction involved, and you take this, let's say there's no magnet either. If you take this coil and arrange it in a way where there's negligible friction and spin it, it's going to keep on rotating due to just conservation of angular momentum. But now let's say we place a magnet here. It's going to stop rotating fairly quickly. And the reason why is we're creating the flux is changing in this loop. And so that's going to create a current in the loop. And remember, currents create magnetic fields. There's going to be a torque on this loop due to the interaction of like the magnetic field it created with this external magnetic field. And so again, if we can remove friction from the picture, with no magnetic field here, you rotate the coil, it'll just keep on rotating. But now you place a magnet here, that's going to create a current that is going to interact with the external magnetic field, which will result in a torque that will slow this down. And so if you want to keep this coil rotating, you have to supply energy. So one of the common ways to do that is burning things and creating steam. And you can force steam to go through a turbine. The high pressure goes through a turbine and it rotates the turbine. That's how we rotate this coil. And then that produces this alternating current. Another way to do this without burning things would be like wind. You can have wind as mechanical energy driving a turbine. You've probably seen those before. And you need to supply energy to rotate this coil. You might think, what about nuclear? Same thing. They use nuclear reactions to heat up steam and run it through a turbine. So almost every form of energy that we use involves Faraday's law. Just using mechanical energy to rotate a coil, and then this arrangement converts that mechanical energy into the energy that is carried by the currents. Now, one notable exception to this is solar power. Solar power is more of a direct current. We just take energy from the sun and turn it into a direct, like the voltage we get is constant, as long as the conditions remain constant. So that would produce a direct current, or DC. So here we produce AC. Something like solar would produce DC. Now, there used to be a big debate between Edison and I believe it was a guy named Westinghouse about which is more useful, alternating current and direct current. Edison thought direct current was more useful. Westinghouse said alternating current is more useful, and Westinghouse proved to be correct. There's one really fundamental difference between alternating current and direct current. And we're going to actually talk about that on Wednesday. There's a particular device, but there's something you can do with alternating current that you simply cannot do with direct current. That's extremely important. And basically, we'll talk about that on Wednesday, but you can change voltages very quickly with alternating currents, not with direct currents. So that allows us to have a standard. Like in the US, if you plug something into an outlet, you're typically getting 120 volts. And I think it's at a frequency of it's either 50 or 60 hertz. I don't remember the exact value. Now, you might have some outlets in your house that are designed for 240 volts. Like washing machines or maybe refrigerators. Some appliances require higher voltage. And yeah, the electricity that comes to your house, it's called like three-phase electricity, where you can connect it in different ways to like 120 or 240 volts, but typically 120. And say that, say you plug something in, maybe the device you plug in only wants 10 volts. It's designed to operate at 10 volts. Well, there's a device called a transformer that can change that. You can put a transformer in between the like the outlet and the device, that'll convert that 120 volts to 10 volts with no problem. And well, I mean, the transformer would actually be built into the device. So if you have a device, you know you're going to use it in America, and you know you're going to plug it into a 120 volt source, you can design it appropriately so it'll get the right voltage that you need. If you go to Europe, they have a 240 volt standard there, or maybe it's 220, but you know, something like that. Now, we're very fortunate though, to hear a lot of countries actually have different standards in the country. So it'd be like, imagine different states, you know, like in Illinois, we use 120, and say you go up to Wisconsin and they use 240, that would be extremely inconvenient. And I've heard that in some countries, even an individual city might have different standards, depending on like where you're getting your power. So it's good that we have a standard, at least, that's universal in our country. But we'll talk more about that later. But another thing useful about alternating current is that's pretty much how we produce power, almost entirely with alternating current. And another thing that's nice is we can actually convert the two. Like if you have a direct current, you can turn it into alternating current. You have an alternating current, you can turn it into direct current. So you can also switch, like a lot of devices want a direct current. So you plug it into an outlet, you get alternating current, but then you have to convert that into direct current as well as maybe change the voltage. So alternating current is very versatile. You can change the voltage, change it into DC. So it turned out to be far more useful. And one of those rare cases where Thomas Edison was just wrong. His argument was that alternating current is more dangerous, which actually is true, but still it proved to be overwhelmingly more useful. Now, I just want to talk about one more thing, since we're on the subject of alternating current. Well, it's constantly changing, and it's changing very rapidly. We're going through like 50 or 60 cycles every second. And typically what we're interested in is like the average value. Now, the problem is if we take the average value of something that looks like this, what are we going to get? Well, we're going to get 0, because the sine function is this perfect symmetry where this branch is exactly the same as this branch, except, you know, they're inverted. And so if you take the average value over a long time period, like if you look at some time period, like say just up to this point here, well, you'll get like this part here, well, these two parts will cancel, you know, this little piece left over. But if you look at a very long time period, you're always going to have a tiny piece left over, but that'll be insignificant over a long time period. And so generally taking the average gives us 0. Well, what good is that? We have to define average in a different way. So we define something called the IRMS value, where RMS stands for root mean square. So basically, the idea is the problem is, 0 is the average. That is true, but it's not useful at all. So we want to have another way of defining an average that gives us an actual result we can use. And so the problem is that the current, I'll do this, the voltage or the current, either one is, they're going to look the same. So the problem is that we have both positive and negative values. So the process is, first, let's square the current. And if we square it, now we're going to have all positive values. Let me get rid of the device itself. Let's just say we have an alternating current where I equals I max sine omega t. So if we square that, now we have, sine squared is always going to be positive. So this gives us all positives. And now we can take the average or the mean. I'm calling it mean because remember IRMS, the M stands for mean. So once we square it, we have all positive values. Then we can average the result. And the problem is that once we square it, we're dealing with amps squared now. We're not talking about a current anymore. So the next step is take the square root. So we square it to make it positive, then take the average, then take the square root. And now we're back to like amps. And so the IRMS, that's called root mean square. Now the tricky part is taking the average. How do you take the average value of a function? There's actually a kind of nice trick we can do. But first, let's plot it. And let's say we're taking the average over a long time period. Now, in general, the average value of a function so basically what, I'm sure you've seen that in calculus before. Taking the average of a finite set of numbers, simple. You add up all the numbers and divide by the total number that you have. So when it comes to a function, x can be anything. We have an infinite number of things, so we can't really add them up and divide by infinity. But let's say we have some interval from a to b. What we can do is sample the function. We'll look at, we can look at a finite number of points on it and kind of approximate the average. We approximately average to the sum. We can apply f to, like here's one x value, here's the next. We can add up those values and divide by the total number. And let's say the spacing between the numbers is delta, or delta x. So, like going from this one, we jump over an amount delta x to get to the next one, then delta x again. And essentially what we have is n times delta x is about equal to the length of the integral, or the interval from a to b. Now I have that approximately equal to because, I don't think the number of intervals is going to be exactly equal to the number of dots you place there, but it could be off by one. Who cares? And so we can say that n is equal to b minus a over delta x, or 1 over n is delta x over b minus a. So, yeah, n is b minus a divided by delta x. And you can see if we take the limit that delta x is small, this sum is going to become an integral. We can kind of see where this formula comes from. Okay, so now let's just take the average of this function. Let's just take the average of sine of x. Okay, now there's 2 ways we can do that. One way would be to integrate sine of x. And then, well, to be precise, let's just look at one period from here to here. Let's average, or no, we want to average sine squared x dx. And let's do that from 0 to 2 pi. That'd be like one full, like when x is 2 pi, we've completed one cycle. So we can get the average over one period, and that'll be the same as the average over the next period. And again, even if you look at a short time interval, alternating current, we're looking at 50 or 60 cycles per second. So even if you don't have a very long time period, this will give you a good average for IRMS. So one thing to do is just do the integral. Oh, wait. We have to divide by the length of the integral as well. So one thing, there's trig formulas you could use here. I know you don't like trig formulas. I've had some mentions in class that you've forgotten trig. But there's a nice little trick we can do here. So if we look over one interval, I'm going to make a statement and say that the integral from 0 to 2 pi of sine squared x dx is equal to the integral from 0 to 2 pi of cosine squared x dx. Why is that? And that is because sine and cosine are the exact same function, except they're shifted with respect to each other. But if you go over a full cycle, it doesn't matter. Like if you look at the unit circle, the coordinates of any point are cosine theta, sine theta. And as you go around the circle, you're going to get the exact same values if you look at the x or y coordinate. So if this is believable, that the integral of sine squared is equal to the integral of cosine squared, that makes our lives much easier. Because we can replace sine squared x as, let's say, 1/2 of sine squared x plus sine squared x. So again, that's nothing special. If we add that up, we get 2 sine squared x divided by 2. So we haven't really changed anything. But now, because of this, we can replace one of these sines with a cosine. And hopefully you can see the advantage here, because sine squared x plus cosine squared x is just equal to 1. So let's take the 1/2 out. So we have 1 over 2 pi. Let's take the 1/2 out. And then we have the integral of 0 to 2 pi of 1. And so that's going to be just 2 pi. So sorry, I forgot this I max everywhere. I was just looking at the sign part, but I wrote IRMS, so we take the average of, or IRMS squared. So we have to, we square this function. And then, let's do this. I squared. So we have I max squared sine squared omega t. Let's just put a line over it. So we're talking about the average value of that. And these two pi's cancel out. So we have I squared, the average value of that is I max squared over 2. These two pi's cancel out. We get I max squared over 2. And then the RMS value is just the square root of this. So the RMS value of the current is the maximum current divided by the square root of 2. And when you plug something into the outlet, the 120 volts, that's the RMS value. So the peak, or 120 volts, the same thing would apply to the EMF. So yeah, the RMS value, let's just say average voltage you get, where we understand we mean the RMS value. That's a peak value over the square root of 2. So this is 120 volts. So the maximum voltage you get from an outlet is typically around like 170 volts. It's the RMS average that's 120. Then just one more thing. Power is current times voltage. I'm going to erase this. So power is current times voltage. And these are both functions of time. So here we have I max sine omega t. Let's say E max sine omega t. Call that P max. Or no, let's call that, be a little careful. Let's just call that P naught sine squared omega t. And because that is always positive, we can find the average power. We don't have to do this RMS thing when we're talking about average power. So let's call this P max, because it is. So the average value, again, just the average of sine squared, we already found out that that is 1/2. So the average power is going to be the maximum power over 2. Just kind of, we can write this in an interesting way. I'm going to go back to I max and E max. So it's this over 2, but let's write it as a fraction. Or, I'm sorry. So yeah, we had, that was max and E max. So the average power, we can write it this way, where this is the RMS value of the current. That's the RMS value of the voltage. And so the average power, kind of out of room, yeah, power always flows in one direction. And the average value, not the RMS, but just the overall average value, that's you multiply the RMS averages, you get the average power. Okay, well, maybe I shouldn't say power always flows in one direction, but in the case we're considering, it does. Okay, so that took a little longer than expected, but are there any questions on anything we talked about today? See, I'm very close to being done with the homework. I am going to post that hopefully tonight. I'm just finishing up one solution before I actually assign it, so I know exactly what I'm assigning. But yeah, I guess that's it for today. If there's no questions, I'm going to stop recording. And yeah, I'll post these links